Okay, so we've just passed our first interoperability test,
Yep.
which was being able to project from this computer. So that was a good practical test to get us started. So my name is Stephen Hosford. I'm working for the Committee on Earth Observation Satellites. I wanted to start off by thanking our organisers from Planet and Radiant Earth. CEOS has been working for a couple of years now on analysis-ready data, thinking about all the subjects that we've been discussed over the last day or so. And we're really happy that there's a swell of interest also coming from the private sector. And I think one of the themes that I'd like to put across in the presentation is how we, in the space agency side, the institutional side, help the private sector reaching new users and kind of getting out of the traditional sphere of where Earth observation data has been up until now. So I have a number of co-authors on this presentation. I'm actually presenting on behalf of a group within CEOS, which is called the Land Surface Imaging Virtual Constellation, which has been around for a little while now. And that's led by three of the co-authors here. Adam Lewis from GA. So we had a presentation from Leo yesterday, who's working with Adam. Jen Lacey from USGS, and Susan Mecklenburg from ESA. So these are two of the big providers of data and one of the big users of data, we'd say, land surface imaging data. So, as I said, I'm coming from a slightly different perspective, I think, than perhaps a lot of you guys. I hesitate to use the term old space, but I suppose we could say old space compared to new space. The institutional side, the Committee on Earth Observation Satellites. I'm going to start by talking a little bit about the context, the way we're seeing the EO ecosystem evolving, and a little bit how CEOS has been addressing the question of harmonization. I'm then going to set out what's been done so far in this CEOS analysis-ready data for land, CARD4L context, talk about the framework, and look at a little bit about how that is moving forward and the way it's going. And then I'll put up a few takeaway messages for everyone. So just very briefly, context on CEOS. So CEOS is the Committee on Earth Observation Satellites, as I said. It's a forum which brings together all of the major international civil space-based Earth observation programs. So we have all the big space agencies there. There's around about 60 members overall. Within these 60 members, there's 151 missions that are currently flying, and even more currently under development. So it's really an area where there's a lot of it's a talking shop to an extent. It's a forum for discussion and for exchange. It takes the form of a number of pretty large meetings over the year, and specific meetings on different groups. So I'm not going to go into detail about the structure, but just to say that on this subject, we have in this little corner here the Land Surface Imaging Virtual Constellation, which is very relevant to this subject, and the Future Data Architectures group here, which is an ad hoc group which has been spun up just to think about this particular subject of where the EO ecosystem is going. As I said, this is a big group. We have a lot of decisional or high-level representation from the people who are taking the decisions on where Earth observation missions are going over the next years. These tend to be the heads of Earth observation programs that are coming along to these meetings. So focusing then on the land surface imaging group, as I said, led by ESA, USGS, and Geoscience Australia, and within that group there are around about 12 agencies who are operating, or still operating, I would say, missions that are generating a large percentage of the land imaging data that's being acquired today. And one of the objectives of that group is to facilitate a maximum amount of utilization of that land surface imaging data. Also through promoting the use of common standards and making those products both more easily discoverable and also ready for analysis. So we've seen that the objectives of space agencies in general tend to be to develop the use of space. And I think one of the things that one of the messages I need to get across today is that the ultimate aim of that is to facilitate the use of space technologies in the general public's everyday life. That necessarily doesn't only pass through space agencies developing missions and operating missions. It has to be through private industry developing their own the capacity and the Earth observation programs. So there's increasing private sector investment in Earth observation, and that means that the role of space agencies within that is evolving. But the question should really be, especially in this area of land surface imaging, where does that role take us to, and how do we support that development? I think if we look at invested dollars over time, the public sector investment over time, I'd say, is pretty flat, perhaps increasing slightly. And we should at some point see the private sector taking over and developing their own systems and making systems that are self-sustaining. So I'm not going to suggest where we are on these curves, but that would be the ultimate success for the space agencies would be that this becomes a private domain, and that there's a development in the private sector. But to do that, we've got to also work on questions such as harmonization. So harmonization is looking to make consistent and compatible things that come from different sources. CEOS has been working on that at many levels for many years. I suppose one could say that if we've been working on it for many years and we haven't got the answers yet, then that's we've not been very successful in that. I'll not say that too loudly because Greg will probably get up and hit me or something. But the objective of that harmonization has got to be to simplify things, simplify the access. And I think this is particularly coming into focus now because we have a potential disconnect between new users, and the huge amounts of EO data that are out there. So if we take a step back and look at land imaging maybe in 2006 or so, middle of the noughties, we had very few missions, well, maybe 5 or 6 that were generating land imaging data. We had scientists that were interested in that data, and the process was pretty simple. The scientists generally knew who to call up or who to send an email to request data from a given mission, and there was some well-established process in each agency where they would vet these science requests that come in and provide data back to those fairly limited group of science users. Of course, this is changing a lot. This has changed a lot over the last few years. Ignacio, would it be possible to get a drink? Glass of water? Thanks. So if we look at that, a very simplified view of this is a simple data generation layer where we had very straightforward ground segments, and what we call an exploitation layer where the science users, where expert users used the data and were able to either do the science they wanted or do the application projects that they wanted to do. That situation obviously is evolving to a large extent. We've got a lot more and much less sophisticated users, so the general public and decision makers. And And we also have, on the data generation side, a lot more missions, and those missions are generating a huge amount more data. So we have a situation where we're moving from small data with very few sophisticated users to a very large amount of data and many more users and many less informed users and less I wouldn't say less educated users, but less specialized users. So this is the situation that we're looking to address with analysis-ready data, because we've got a situation where the complexity is increasing and we're having a potential disconnect here. So we've got to simplify the products in order that those large number of users can actually exploit the data. Cheers, thanks very much. So we saw this a little bit earlier on. From one of our European colleagues. We also have a complexification, if you like, of this environment. So we have the initial data generation layer. There's just some examples of names of people in here. It's not exhaustive at all. And we have the exploitation layer up here. What we've seen is new entrants into this area. So a layer which we call the resource layer. So that's infrastructure. So people like Amazon, Google, and some others. And also, sitting on top of that infrastructure, we have people that are offering platform services or platforms and different services layers, and there we can see many of the people that we have around the table today. We also have institutional actors coming into that. So we have the DSs in the European side, and some of the national platforms. And also we have some investment in national and institutional investment in the platform services as well, with things like the Data Cube from Australia or the exploitation platforms that have been developed in Europe. So we can see that the EO ecosystem is more complex, and one of the ways of, as I said, of trying to combat this potential disconnect between the huge amount more data and these new users is addressing that through analysis-ready data. I think maybe one of the messages also that I wanted to get across here was that, and has not really been mentioned up to now in the discussion, people have been hinting at it, but it's not really come through, is the idea that in order for it to be analysis ready, we need to have defined to an extent what the analysis is. Nobody's actually come through and said that. They've said analysis ready for what? But in this case, where CEOS has worked to define analysis ready, they've looked at the land applications. So they've identified what the analysis they anticipate this analysis-ready data will be used for. And I think that's probably an important qualifier going forward. You need to say what analysis you're anticipating your data will be used for. You can't just say analysis-ready, but it's too general. So setting out then a little bit this framework, this CARD4L framework that's been defined by the Land Surface Imaging Group within the CEOS. So CARD4L is satellite data that have been processed to a minimum set of requirements and organized into a form that makes it easier and involves a minimum amount of effort on the user side. This definition hints also at the fact that this should facilitate interoperability, but we'll see, so on the time aspect that was mentioned in the last presentations, but we'll see that the framework itself doesn't actually take us very far in the interoperability aspect. It provides a framework, but it doesn't actually. It's not prescriptive on the methods used, and therefore it doesn't help us that much on the interoperability side. So, going into a bit more detail, the definition of CARD4L, as we've just seen, was then broken down, and a number of specifications were developed for product families. So up until now, the first product family specifications that have been defined are for surface reflectance, land surface temperature, and radar backscatter. These are not entirely finalized and as yet. Some work remains to be done on them, but they're well advanced. These product family specifications are technical documents. They're available for review, and you can look at them. And there are another set of PFSs specifically for radar products that are currently being discussed at the minute. So things like polarimetric covariance, INSAR products, and such like. So there's one radar product that's been worked on and been developed so far, and these additional products are currently being developed in order to try and bring out some of the other aspects of radar products that are perhaps more complex for these less expert users. I put the link up there so you can go and have a look at those documents. So the products family specifications are defined. There's then a assessment process for different products, including a peer review process, and ultimately there will be a kind of stamp provided with two different levels that are defined within the specification. One threshold level, which is the threshold, obviously, and then a target level, which sets slightly higher constraints on the product. Looking a little bit more detail on the actual contents. So there's within the specs, the requirements are for general metadata, providing information, for example, on lineage, and then an information on a per pixel metadata. So something that's been discussed a lot up until now is information for each pixel saying what is the quality of this pixel. So that's an important information. How suitable is this pixel to be used for a particular purpose? Information also on what the pixel is. For example, for surface reflectance, measure of the land surface. That what is the pixel integrates the aspects of radiometric and atmospheric corrections. And then the question of where is the pixel, so that integrates the aspects of geometric corrections. So it provides constraints on how well the pixel is geolocated. For example, to give an example between threshold and target, for the geometric corrections, the first is for threshold is a relative accuracy, and for target is a absolute accuracy. So these some of the ways that the different levels of detail that are provided in those specifications. So you'll see that, as I said, none of this is prescriptive. We don't say in this framework you have to use such and such an atmospheric correction in order to have this label. We just set a certain level of accuracy or precision, and associate also the information that needs to be provided in terms of the documentation on the algorithms that are used, etc. So it's not prescriptive, and it doesn't. So in that sense, it's inclusive. But that's what I was coming back to the question of interoperability, because of the fact you're not going to that prescriptive level. The question of interoperability is not as addressed as far as it might be by some other approaches. Okay, so if we take some examples then, so from the different sensors, Landsat, Sentinel-2, the sensors that we've heard a lot about, ALOS and Sentinel-1 for radar. So each of these different sensors then provides data that can be either surface reflectance, surface temperature, or radar backscatter families, and generates a ARD product for each of, that can fit into each of these product family specifications. So as a summary then, this is a label, a kind of label that's been defined and monitored by CEOS agencies through the Land Surface Imaging Virtual Constellation. The idea is that this is a living document, a living specification, although the control of that and the way that that's evolved initially is thought to have been anticipated that it'll be controlled by the LSIVC. However, the idea is to remain, to have a PFS that is as stable as possible over time. Another aspect to this is the fact that we've begun to do a product stock take. So there's also a document that you can consult online which lists all of the potential Card4L products that are out there currently, so including things like obviously the Sentinel-2 and Landsat data sets that are out there. So just to wrap up then, a few takeaway messages. So the institutional space sector is and has been over the last few years addressing interoperability of land surface imaging products through this CEOS ARD for land. The idea, the main objective is to facilitate uptake of space data by these new users, try and reduce this disconnect that could happen. We think that this Card4L framework should help intermediate users, intermediate private users that might set up platforms, for example, or data cubes to serve AO data to their users. I hinted at it a little bit also, but the private sector, feedback from the private sector is obviously very important for space agencies. The ultimate goal, again, of space agencies is to have space technologies used by as broad a set of users as possible. And there's a desire to have that synergistic public-private approach. So one of the big questions for me in coming to this workshop is, how can space agencies help the private sector develop their activity and do their work and reach the users they want to reach more effectively? So I just finish up by saying we're very interested in feedback for Card4L, so please get in touch if you have any comments. Thanks, Ignacio. Questions at the end? Yeah. Do you need the interoperability or not?
Yeah, exactly.
Is there a VGA or?
It always needs an adapter.
You gonna be okay using your computer?
Yeah. I wasn't sure what I needed. Mute's off. Mute is off. How about that, right? Yeah. Oh, look at that. I've forgotten. Yeah. That's a really cool satellite. Okay, I'm George Percivall, serve as the CTO and Chief Engineer of the Open Geospatial Consortium, and I'm going to speak more about the other side of ARD, and that is the access and the pull and the application and getting it to the users and the like, even though I do have a little bit of background in remote sensing. And so in that regard, I'm going to talk about remote sensing and GIS, and of course I'm going to base it on open standards. I'm going to put ARD in the context of data cubes. So OGC, the Open Geospatial Consortium, we've been around for about 25 years. We got about 525 member organizations from around the globe, from the triple helix of universities, government and commercial organizations. We've got about 40 standards, hundreds of thousands of data sets served up through OGC standards, compliance test suites, that kind of stuff. So we're an open forum for the development of interoperability associated with geospatial data. That's OGC. With respect to why this is interesting and the conversations we've been having in the consortium and what I've been learning today as well, yesterday and today, has to do with more from the data cube side. So, a couple of years ago, Australia, I think really kind of wowed me. IGARS in 2013 was in Melbourne. I don't know how many people were there. Yeah, you were there. Of course you were there. It was just, wow, that's a really cool way to look at Landsat data in time with a drill down to be able to look at pixels and say, what's the water history of a pixel, and do it in, rapid fashion to be able to get an answer that's really interested in time history of water pixels. That depends upon ARD. Didn't realize how much until we got into a little bit more discussion. So that's one perspective about data cubes and ARD that came into OGC. The other one is a little bit more from the weather community. ECMWF, the European Center for Medium Range Weather Forecasting, has worked with a variety of companies, including companies and agencies, NASA included, on what's called a data cube for Earth server. It actually says 2.5 petabytes to 220 petabytes. I'm still skeptical about that number, but I know it's huge, multiple petabytes, although petabytes aren't as big as they used to be. This is actually a little bit different, right? You can wear them on a backpack. You can put a petabyte in your back right now. So in any case, data cubes as a functionality as opposed to an implementation is what I want to focus on, because we see several different implementations of data cubes providing that analysis ready for applications and consumers and the like through a set of interfaces. And to some degree, the underlying implementations don't matter to the end user because they have interfaces and they can work with the data. And so that's the perspective by which we've begun to develop an outline of discussion topics, a paper, regarding to geospatial data cubes. So of course we have this whole data cube is just a data structure. Some people want to put that into things like RDF. That ain't what we're doing. You're not going to put all that imagery in RDF, for example. We're talking about data cubes as in what I just talked about, the Open Data Cube or the Rosdaman kind of data cubes kind of stuff. And so why do we care? We care about interoperability. We've also talked about federation, so that you'd have multiple data cubes, different regions, different purposes, and yet they would still be able to create some value through federation. And that would include things like naming, so that if you go to the different data cubes and ask for a product, you'd get the same value, you'd get the same geophysical parameter kind of stuff. I'm going to talk about the information model, which is based on what's called coverages, in particular geospatial coverages. I'll talk less about data preparations and ARD. It's really important. I've been amazed by the conversations here. I've learned a lot. I'll give a little bit of reflections about ARD. Analytics is much more what I think is, from my perspective, it's, how do we bring value to those end users? It's the analytics that you can perform on those data cubes and ARD that brings value. So I'll speak a little bit more about that. And of course, interoperability, APIs and encodings is the payoff. To give a perspective on that, I got to talk about interoperability of remote sensing and GIS, because we're a bunch of remote sensing folks in the room. We've hit on a little bit about kind of GIS. Will's talk from Will Cadell, great talk about embedding stuff. The lady from Climate Corp with Cropscape, not Cropscape, that product, and showing how for the farmer you got to put it in the pad of the farmer along with a bunch of other data. Most of that data is GIS data. And so how do we achieve interoperability between remote sensing and GIS data? They're two different worlds. I continue to be amazed at how much there's not enough overlap. I just read a history about GIS, included something called naive physics, kind of interesting. It doesn't mention anything about remote sensing in the history of GIS. And I'm like, really? So, one of my missions in life is to bring that Venn diagram a little bit more overlap, Two areas that I'll speak about that interoperability is maps and data. So in an OGC speak, map is WMS and WMTS, and in data, it's the coverage model. So let me speak about those a little bit more. So going back a little bit, WMTS access to Landsat in 2004 used to be part of a NASA office called the Geospatial Interoperability Office. It was previously called the Digital Earth Office. We got a bunch of Landsat data that came through Stennis as the Landsat Science Data Buy. 8,500 orthorectified Landsat 7, mostly cloud-free scenes. 8,500 because that's what it takes to cover the land surface of the Earth. Those were shipped out to JPL. A guy some of you probably know, Lucian Plessa, now with Esri, did some amazing work back when it was HPC and supercomputing, before we talked about clouds and all that kind of stuff. He developed an amazing WMS, WMTS mosaic server, demonstrated at the United Nations in 2002. It's been operational until it was replaced by this, which is GIBS, Global Imagery Browse System. Amazing system in the sense of, you can get this access to the amazing amount of NASA data using a real simple protocol, web map tiling service, WMTS. And so all kinds of data available to a lot of clients that you usually don't work with, the GIS clients, right? So OpenLayers, Google Earth, NASA Whirlwind, all of those can access that. So really impressive. One of the key things that shows up in here in the WMTS spec is what's called the tile matrix set. And so this is now a standard. It was part of WMTS. It's been pulled out and made separate. So one of the things that Chris Holmes hits on a regular basis is what are those little pieces of things we can agree on that can be used in many different locations. And it's some things like this, the tile matrix set, which is, we all deal with this, right? But it's getting the language and the agreement about how to encode tile pyramid and the reference into a CRS and an encoding that can be shared across information systems. So it's kind of dead simple at this point. It's kind of like, yeah, well, okay, we all agree about that. That's a success story, right? And so now it's pulled out and it's available as its own standard. It's used in something called GeoPackage. If you've heard of GeoPackage, WMTS can be embedded in there. And it's an example of this building block approach that Chris would talk about. So that's maps and an example of how standards coming out of a development eventually get set. That's one of the themes I headed towards is how might this end up informing the development of open standards. So we talked about maps, let's talk about data. Data is coverages. Didn't know this was animated, oh boy, let's see what happens. So in trying to find a generic model that allows us to talk about geospatial data of the type that we work with in remote sensing, there was a development a few years ago of what was called coverages models. It came out of the research community, ended up being standardized through a series of OGC and ISO standards, now known as coverages. And it really is a model that says you've got a point on the Earth and you want a piece of data about that. So if the point on the Earth is well described in terms of where it's at, it was a CRS, coordinate reference system, and there's a mapping. It's a mathematical analogy that you can point there and say, tell me the record of data, record in terms of some vector structure or even a grid or a tensor about that point. Pull that back. That's the notion of a coverage. It may be structured as a continuous coverage, like something you can ask of an analytical expression and get a value at any point in that space, or it can be a discrete coverage, like an image. You have a grid or a pixel, and you have a value for that location, whether it's at the center of the grid or it's pixel in the corner, all that kind of stuff. But it's mostly discrete coverages that we deal with. So a very robust information model about how to make the stuff you guys deal with in remote sensing accessible to a much broader community through standardization around coverages. We built a access paradigm associated with that, put it on the web, called a web coverage service. That's what WCS is. So it allows you to ask for specific parts of the data set that you're interested, lots of server-side processing implied, bring back only the data that I want, right? So that's the key thing of that. Analytics then on that server side, on the WCS. After you slice it, do some analytics, and then give it to me, right? So this is a coverage processing language, which has now made its way into the SQL stream of standards. There's now called an array database extension to SQL in the ISO JTC1 community that does this coverage processing language. So you can ask for coverage processing, raster processing in a well-formed SQL-like way on that remote server and get back just the information you want. I think this is an NDVI. Everybody loves NDVI. Which NDVI? But you get the idea. So the other thing that's relevant is gridding systems. We all love gridding systems. New standard is a description of discrete global grid systems. So these are grid systems which are not troubled by, I don't know, poles and date lines like all the map projections are, have really efficient processes with respect to tile pyramids. So you choose a cell structure, you choose how that tessellates the surface of the earth, you figure out a resolution pyramid that goes with that. You have a very efficient and useful and interoperable way of describing the grid that you're going to do analytics on. So it can be very useful in this context as well. So that's the parts that we bring, maps, coverages, coverage processing language, and discrete global grids. Let me give a little bit of discussion, kind of reflecting on what I heard yesterday and somewhat to today about ARD. And it really is this ARD is an endpoint or ARD is a starting point. ARD as an endpoint is, I've done all of this processing to give you this product, right? It's here it is. Here's this analysis ready data product that had to go through a whole lot of processing, the variability for each product though. There's no single ARD. It's whatever needs to be done to get that data ready. That's one perspective of delivering it, and here it is, the endpoint. The other side of it is as a starting point. Oh, you got ARD? What can I do with that? What are the analytics that I can actually now perform on that ARD? If it's analytic ready data, what analytics were you thinking of that I could process on that, right? So ARD from that point of view is more about, what is the query language or otherwise that you put on the analytics? Is there consistency across sensors, or is it more about the environmental parameters that we're concerned about, or that what end users are concerned about? This environmental data records or climate data records, and then some agreement on geophysical parameter names and meanings and like, especially for the federation stuff. So, the remaining part then here is about how do we separate those two parts in some way. This is a presentation from 2 weeks ago at IGARS in Europe. And by Chris Linus of NASA, ESDIS. And you can see how he's structured first ETL, so not a remote sensing term. I was amazed when he put on there. It's usually a data processing or GIS term, but he clearly separates the analytics optimized data store from the analysis itself. It's still in the cloud, still cloud analytics. Should we separate those two? Should we talk about it as separate ARD versus analytics? We've had some earlier discussions about that. Or do we bundle them together in some way? The other thing that's coming up in the OGC discussion is we've begun a discussion about exploitation platforms. One of my ESA colleagues leading up the formation of this working group to look at exploitation based on the TEP and other activities, has some traction around the globe about that. So, maybe it's a separable concept. Maybe we define ARD as a data set and analytics as separately. Somehow I think there's got to be a combination between those two. So we've talked about a lot of things that are happening here. Let me leave you with one thing, and it's not only relevant here, it's also relevant and maybe more immediately relevant for STAC. And that is the relationship between innovation and standards. So at the end of the day, what I'm interested in is, your best thinking turning into something that somebody else uses. And so how does that happen? How does it become a standard that's commonly adopted and the like? You start out, this is a state diagram kind of thing. No standard exists for the marketplace, right? There's a couple of different ways this can happen. One is somebody, a company in particular, does a really good job of defining something that becomes a de facto standard. And it's public, they publish the spec, but it's proprietary in the sense of they control the intellectual property. They'll listen to your request, and maybe they will, maybe they won't change their spec, right? So that's over there on the right, public but proprietary. Sometimes that gets labeled as open. It's my job to tell you in the definition of OGC, that ain't open, because open consensus standards mean not only is it public, but it has a process that allows anyone to ask for a change request, and there's an open process by which that spec gets updated. And so sometimes those specs, those public but proprietary standards, the intellectual property gets turned over to an organization like OGC with that kind of standard setting role. I commend Google. They did that with KML a few years ago. It's now in a standards working group in OGC, which Google chairs, but it's an open consensus standard. The other branch, number 2, is that it's developed kind of anticipating that something is going to need to be done in this space. And so from the beginning, that intellectual property is available to all and shared and the like. So that's kind of my little riff on where I hope we go coming out of here, and in particular, what may happen with STAC as we move forward. So, okay, that's where I'll leave it, and we're going to do questions afterwards, right? Thanks. Before I walk to the restroom. You go?
Yep. All righty. Put it here. It's content to there. There we go.
Cool.
I think it's on.
Thank you. That's not exactly what I was intending to show up there. All right, that's a little better. My name is Tyler Erickson. I work on the Earth Engine team at Google. And so I'm going to give you just a short kind of perspective of how we view kind of the term analysis ready data. Going to go very briefly through what Earth Engine is. Anybody feel like they don't know what it is at this point here? So I will be really brief, I guess, at this point. It's our cloud system for doing geospatial data processing. It's built so you don't have to be a computer scientist. We're trying to address people that aren't strong programmers, but they are generally programmers at least. It's a lot of academics, NGOs. We're trying to do a lot of work that's working on societal, environmental, social issues that are global in scale. So we're not generally for consumers and we're not generally for businesses. We're for this yet other group, which is more like NGOs and public benefit organizations. We basically co-locate a lot of storage of geospatial data sets along with geospatial algorithms and a lot of computers. We're not really limited at Google in a lot of these, so we have a lot of flexibility for doing that. It's very much customized for geospatial data and a certain type of it, a regularly gridded raster or vector data, points, lines, polygons. And then we expose it with APIs for a variety of different clients. If you want to know more about that, there's a remote sensing environment that goes through the underlying details of like how we set up the system, how we design for scale that you can look at for there. Underneath the hood, we do this concept of having data sets and a kind of a directed analytical graph that describes the processing of those data sets and the algorithms that are applied to them. So a user can apply one of our 1,000 or so functions to these data sets, or you can construct your own custom functions by chaining together quite a few of these terms. A lot of this is lazy, inherently parallel, so we can do stuff really fast when you're doing algorithm development, like on the fly. But then when you want to kick it off and run something for a continent or the world, we can do that as well in terms of a batch process. We have right now around 200 data sets, 10-ish petabytes of data, depending on how you count it. Simon, who's over in the STAC group, is our data wrangler, so he's the one that manages all these pipelines. A lot of it's just keeping up to date with whatever is going differently at USGS or the Sentinel hubs, or et cetera. trying to keep those data sets flowing into there. But it amounts to around 5,000 or more images each day that we're ingesting into the catalog. In addition, as I said, we have about 1,000 of these algorithmic primitives that we can apply to these data sets. And what's kind of nice for us is that we will start with a data set that is provided by somebody like USGS, NASA, et cetera. That's kind of our starting point. It's, it's processed to their level. And then we can do some things on the fly to make these virtual data sets. So anything that's like band math, image masking, spatial sampling, resampling, temporal aggregation, a lot of these are just, they're listed in our catalog, but they're not stored anywhere. We basically just do that type of operation on the fly. And so somebody can treat it as just a static data set. We have a JavaScript and Python API built on top of this RESTful sort of, or REST-like web API. And on top of that, we maintain what's known as the playground code editor for using the JavaScript API. It's what we use for teaching. A lot of people start off that way. And then when you need more flexibility in your analysis, we direct them often to the Python API and use a lot of the open source tools to work with that. Here is, I was going to go, I guess, a little bit into how it works, but it sounds like people mostly need it, know it. And if you want to go, I linked this presentation, made a link at the beginning and at the end, and it will be sent out. So you can just play around with it. This is like a snippet of code that's 16 lines of code. It goes through Landsat 8, all of the imagery, filters it to a certain time, calculates NDVI on it, plots NDVI in a true color representation, and does a chart. And that's like 16 lines of code. So it's sort of like an ideal algorithm for us. Some of them are more complex. They might be hundreds, occasionally like thousands of lines. Then you're starting to get really hard to debug what it's doing. But our goal is to make it an API that you can do things like this at scale really easily for doing these type of spatial and temporal aggregations. Okay, so general thoughts on ARD. First one is that a lot of these data providers have been doing this for a long time. They just didn't call it ARD. They've processed stuff to different processing levels. The different processing levels are appropriate for different analyses. We tend to use, if you look at the NASA data processing levels, the level 3 and level 4 is usually the ones that we bring into Earth Engine. For Landsat, it used to be the L1T, now it's the Collection 1 data sets. It varies. But basically, we're looking for something that is on a uniform, regular grid. Doesn't matter what the projection is. That's usually our base raster data set in Earth Engine. And then everything else is usually done on the fly on top of that. In terms of what is ARD, to me it seems like it can be a lot of things because a lot of people want different processing steps. Here's just a few of the ones I took off the top of my head of thinking of the processing steps that people will apply to this raster data. And I only thought that the first two are kind of non-contentious, as like we want those always. And then anything below that, sometimes it's still research in terms of like what is the best way for this. There's so many cloud shadow mask algorithms. They're sensor dependent, atmospheric correction as well. So a lot of these, I can't really see we coming to an agreement on one ARD product because there's so many different choices at any step of the way here. And it's important depending on what analysis that you're doing too. We might get an ARD product that is good enough for 80% of folks, but I would love to preserve kind of that flexibility for people that actually don't want to go with all the defaults. When you get down to the area of multi-source estimation, using different sensors and combining that into your algorithm, that's where it gets like combinatorial, more complex in there. And that's the area I think that is really more exciting for the future because I view a lot of this remote sensing is that we just have sparse observations that are distributed in space, time, and in the spectral bands, but we're really trying to get estimates of some continuous phenomenon that's going on. And if we can take advantage of multiple sensors that have different characteristics in space, time, and in spectral, it's going to be a lot more powerful for coming up with the end result. This is just kind of my graph of like, as you go along the levels of processing, you're going to keep some users happy once you get through radiometric and geometric, and you gradually get a couple more happy users as you come up with some solution, easy solution for the rest of these. But then you're also going to have a bunch of unhappy users that don't like your choice that you made for all of those different ones within there. Going back to this task graph again that we go through, this is my idea of like sort of what ARD is. Like any little box in there could be the starting point for somebody's analysis. And we are very open about how we did that in Earth Engine, like publishing the paper, and love to talk about it. I'm excited to note that OpenEO, who is mentioned a few times in here already, is trying to more generalize that they will be an open API that could use Earth Engine under the hood or other geospatial processors or the backend. And I like this idea of kind of a standardization of an API, even though there may be other or different implementations, different data sources, different algorithms behind the scenes. Another thing I wanted to point out in terms of interoperability, I love these ideas of containers. I love when USGS went to publishing a Docker container, because that allowed us to help them out in a sense with their Landsat processing. If they were backlogged by how fast they could process to surface reflectance, once they published this container, we didn't have to wait for them. We could actually use their container and just apply it to the raw data. So I really like that approach, and it's really nice to see how that can be used to scale across. If you have access to a lot of machines that can run things like Docker containers, it's a good way to make things repeatable so that you can share kind of the processing burden around. And that's it. Try to be quick on this so we had more time for questions later. Do you want this back?
Why don't you keep it? All right, any questions? We have the mic open here. Let me see. I mean, I guess I have a first question. We've been talking about interoperability, and I think, I mean, I like your note on closing on containers, and can we start standardizing containers or appliances that capture the different steps in a way that people can literally, you know, check out of a library their containers and, you know, execute them on their own? Is this something we can commit as a community to always publish algorithms in a containerized, standardized form so we can choose how to deploy them in the cloud? Do you think that has a future?
I like it, but I'm more interested to hear whether that's common. I mean, we use it a lot for, or at least I use it when I'm publishing user interfaces, like the idea of using a Jupyter notebook, and there's a lot of flexibility of all the libraries that you can use as user interface. I'll put those into a container and share it with people, and then they use that container to access their attention.
Jeff.
So on the Landsat team, we've had discussions about discrete global grids as an alternative to traditional scene-based geometries. And the idea's been around for a long time. It goes back to the 70s, I think, in Santa Barbara and that kind of stuff. Just kind of curious to get other people's perspective on the utility of discrete global grids, and then also ask you, from the OGC perspective, who's adopting it now? I mean, who's actually using it successfully, and how are the tools evolving to be able to access data, manipulate it in that native kind of format?
I can start, I guess.
I guess I need.
And then I'll put Isa on the spot. So, yeah, absolutely. The recently adopted standard is the culmination of a lot of work out of research for many years. And in fact, I've gotten to know more of them as they've called me up and said, "You borrowed my figure and you didn't attribute it to me." Yeah, that kind of stuff, right? And so right now, the standard's been adopted is essentially the framework for any kind of system, discrete global grid system. It essentially has requirements about how to do it and what is a good system. So there's only like 3 different geometries you can use for cells. There are certain attributes of how you do the pyramiding, overlap and the like, and tessellation, containment, and all those kind of things that you should do. Equal size cells was a huge debate, especially given that an ellipsoid, it's really hard to get equal. So we ended up defining the requirement in terms of a limit on the cell size, that in the limit, as it shrank to a sphere, they would be, shrank to a sphere, uniform to a sphere, would be equal size cells, although there's still people that object to that and say you ought to allow, So yeah, lots of good discussion. The next step is to have examples standardized of particular grids. So there's 3 or 4 different grids that are very popular right now in the discussions. One out of New Zealand, one out of Canada, one out of Australia. The one that started kind of with Matt Pearce and the GA activity and the like. And then in Europe, Peter Strobel from the European Commission. Sorry, not ESA, has been very active in advocating the use of DGGS for definition of sentinel activities, and so it'll be interesting to see how that goes as well. So there's lots of good code around and amazing ability to do analytics on the fly. One of the most impressive ones I've seen is Canada being able to identify likely landslides locations based upon a formula that's implemented on like 6 different layers in DGGS and terrain and the whole bit. So it's impressive stuff. I don't know if you guys have any reflections on that?
Mine's a little different. Since it was coming from somebody that deals with the Landsat science team, can we get rid of that overlap as you go along a path between the different scenes? It seems like an area of clouds. It's just pointless. It's
to be in lab.
Yeah. Can we get rid of that overlap?
You want the overlap.
There's information there.
There's no unique information.
Oh, it's different.
It's repeated from
You're
one.
overlap between 2 scenes in a path.
Yes, yes. As you go from one to the other, there's an overlap area.
Like a bit of color for processing, where if you're applying some machine learning algorithm or some other algorithm, you need a few extra pixels on from scene to scene so that you don't get sort of scene.
You could always request 2 scenes and actually use the ones from the next.
Okay, so here's where this is all going to become moot, and that is getting to a cloud-based storage and distribution where people are ordering a specific area of interest as opposed to ordering a esoteric path row for a product.
Yep.
So when we get to that point, which hopefully we'll get to sooner than later, not in this next iteration, but in the next one after that, hopefully, where maybe we'll go to DGGS or something like that, we'll see. But at that point, scenes will become irrelevant because people will use their own areas of interest.
Doesn't the WELD and some of the other USGS systems already do afford a geographic query as opposed to a path row query?
Correct.
Yeah, so
I mean, it's an artifact of the way we stored it and the way we delivered it for years and, for 50 years. And that'll hopefully go the way of the dinosaur once we're cloud-enabled distribution and a lot of smart people with smart APIs better than Earth Explorer come up with ways of search, discovery, and distribution. Or not.
Or not. Yes, or maybe not.
So my question is for Steve Hosford. Thanks very much. You referred to a stamp on card 4L.
Yep.
It suggests that it sounds like a certification, and it suggests that there's a process for certification. Am I assuming too much?
No.
Can you comment on all that? And maybe
Yep.
just talk later.
I can, yeah. That's the intention. I think there's currently a process under definition for doing that alignment with the specification that's been written. And the idea would be that people, whoever, who's got an ARD product, which is surface reflectance, radar backscatter, or surface temperature, would be able to ask CEOS LSI to validate I don't know what the right terms are, and I'm not sure whether CEOS is qualified to do this kind of thing, but I don't think certified is probably not the right word, but the idea would be then to measure the alignment of the product with the specification. So that product assessment process is under definition. It's not entirely finalized, but it's not far away. And then agencies, space agencies who have products would be able to request them to be validated, if you like, and the same thing for private operators. That's the idea. I think we'll have to test run it a little bit, because CEOS has never done anything very operational in that way before. But that's certainly the intention.
Price is right.
Come on down.
So I'm not sure what exactly my question is going to be here, but
Maybe you should go back again.
What's that?
Maybe you should go back again.
No. So I think it's for you, George, or I think it's for you, Tyler. I mean, so it seems like there's two schools of thought around like this: pre-processing and processing on demand. But I wonder if you guys could speak to this idea of like a middle ground, like almost glossary of terms, in terms of definitions. And is there something that exists in OGC that we can start to move towards what the spec might actually look like? What does an ARD spec feel like? And is it a document that just simply describes what's been done, right? And is it standardizing on this idea of level 1, 2, 3, 4, and what those might mean? Obviously, that's a huge issue. But is there a glossary of terms we can come up with, and then use that to say, okay, I have an ARD data set I've been delivered, or they say that it's ARD, but it's done to this level, and here are the terms we've agreed on that describe what's been happening.
Yeah, fair. So I think I saw an ARD spec, and I'm very pleased to see where that's headed.
I thought I talked about an ARD spec, maybe not.
And yet, I'm not sure what he's got answers your question, though. And that is more around the registry of names of geophysical parameters almost. And when we start talking in those, it tends to be more the semantics aspect, registries, naming, labels, linked data, all of those kinds of semantic web capabilities from a technology point of view is what comes to mind from the user's perspective. Because, quite frankly, even though, I have a background in remote sensing, as a user, I don't want to know about levels of processing. If I could never see that scale again of level 0 through 4, I'd be happy as a user because they don't understand it and they don't need it. What they need is a term that says soil moisture or soil productivity, ag seemed to be a really good example here of getting to that end user's needs. One of the challenges that really becomes apparent is there's a big gap between that ARD and what the user needs, and I think it's the combinatorial explosion of what users need versus what the industry and the community can produce makes us think that we can't go there, in the sense of you're not going to be able to prepare a product for every user's end needs, but if at least you could have a vocabulary and name it, you might be able to get to the point that, say, when the user asks in a vocabulary they understand, you could offer something that is probably a good match, because that's what it triggers. So
I would say that whether you do it on the fly or you do it in advance is a separate question from what the definition of what you're going to do. I would just caution you or people not to think we have to store everything and limit our idea of ARD limited by how much storage we have. Because you could define these things that could be generated on the fly for the smaller subset of people that actually want intermediate projects or more advanced products.
I think there's also a difference between on the fly and on demand. It's a subtle difference, perhaps, but on demand, you can imagine a situation where you can, for example, define which geometric corrections you want, which reference data sets you want to use, which radiometric correction approach you want to use, for example, to get a surface reflectance product. And that would be an on-demand approach. And then in implementation terms, that would be done on the fly, right? But on the fly is just an implementation term, if you like, whereas on demand actually identifies you parameterizing the product that you want to get out at the end. So it's kind of it would be a specialist user product, or approach, I suppose. So it's going somewhat against the kind of description of what ARD is. The ARD is supposed to be for general users and not specialist users. But that on-demand approach allows you to be more responsive to user requirements, and it means you don't have to generate, and store all those different types of products that you might have.
Yeah, I definitely agree with that. I would say a good example of that is the cloud masking algorithms. Sometimes there's a threshold, and maybe there's a default threshold that you could process that you wouldn't have to do on demand. You do that in advance. Mm-hmm. But then for some users that want to tweak it because they're in a certain part of the world that the defaults don't work well, then you could allow them to do it on demand.
I mean, there was a post by Chris, actually, that we had interpreted as taking the discussion in that kind of direction, doing a ARD on demand, which was a kind of a parameterized ARD. But I don't know whether that's what he, it's difficult to know whether that's what he was driving at or not.
I mean, I think from the point of view of implementation, what we see is a call from customers to do things on demand. So there's a lot of the metaphors about customizing things that are going to be made on the fly and providing schema for that. And that's one of the goals of the workshop, is to think a little bit about how we standardize that.
All right.
Yeah, I think that this was meant to mean on demand,
actually,
as you describe it.
At ESA, we're currently looking at how we do apply that approach in a very small demonstration kind of phase, and the idea would be to have a little demonstrator of how that can be done, just allowing somebody to specify which geometric corrections, which radiometric corrections are applied to Landsat and to Sentinel-2 products. That also, to an extent, that approach, which is on demand, gets. I mean, some of the difficulties with interoperability. The interoperability aspects are that it's very difficult to get two data providers to agree on what radiometric corrections and what geometric corrections they're going to apply, and so that they apply the same one to the two data sets, to reduce this or to improve the interoperability situation. And if you can do an on-demand processing, that way the user can decide what he wants to apply, radiometric corrections, geometric corrections, etc., and he can apply them to two data sets, and can get the result coming out of that will be more interoperable than if the kind of default situation where USGS produces its own surface reflectance product, and ESA produces their own surface reflectance product. So,
can I question that though? And this kind of goes back to Jeff, what you did with the harmonization in using the same algorithm for the surface reflectance. I don't get that because the whole idea of ARD, as we've defined it in terms of going to a level 2 surface reflectance geophysical parameter, is this is a piece of ground, this is a measured reflectance of that piece of ground, and if you use your method and we use our method for doing the surface reflectance, the truth is the truth. The only difference there should be there is what's your uncertainty of what the number is that you've got there. And so it seems like what you have is anybody can use whatever mechanism they want. It's only, and what you have to have in the metadata is really what's the accuracy of that value, what's the uncertainty that surrounds that value, and you have to have some reasonable means of product validation so that you can come up with a meaningful number for that. And that should be part of the specification, is the way the validation is done. And it doesn't matter how you get the number. It doesn't matter what algorithm you use. It doesn't matter where you get your atmospheric characterizations and attenuation values, whatever sources you get that from. What matters is when you process products and you look at the same piece of ground, that you can say, this is the reflectance with an uncertainty of 3%. And if everybody's got that, then they should all be interoperable from the radiometric.
So I agree with you from a theoretical point of view. My understanding is that doesn't happen. It doesn't happen like that. I think the ASICS process has shown that even when you use the same data with two different atmospheric correction approaches, you get different results out. So,
but then your uncertainty is large. That's
It's more
Yeah,
than
no.
that. I mean, this is about every data set should have a full, let's say, standardized way to represent the covariance. What the user really want to do is a bias variance trade-off, right? They want to sacrifice some accuracy to get more consistency so they don't detect false change in the time series, for example. The question is, how do we encode that trade space so the user can make the decision? In practice, we just don't know how to do it yet. So the only thing is a brute force approach, is a big hammer, which is, well, reduce the variability of this second input, which is, let's say, atmospheric correction. That sensor fusion task of bringing an AOD estimate, that's another input too, that has its own covariance structure and things like that. So it's because we cannot write that covariance schema that we have to resort to harmonizing things by using the same algorithm. I don't know what the rest of the group thinks. It's a very big problem.
To play devil's advocate, I would say there's probably a lot of users that don't care about that covariance matrix. I do, but
I disagree with that quite strongly.
okay,
me too.
okay, good.
they care
the
about
devil advocate.
Sorry, I backed off too fast.
So the reason I disagree with that is more and more machine learning algorithms out there take covariances and uncertainties as an input, as a way of weighting appropriately what it sees in the data and allowing it to make intelligent decisions about things. And I also disagree with kind of the statement that this is a hard thing to do. We can very easily run data through our forward transform, put some variations on it, and we can actually get a sensitivity analysis out of it in terms of saying, what is our error transformation as it goes through whatever processing operations we do. So I've done a lot of work in the past of error propagation. So you can take your data, you can put some variation in it in terms of representing those covariances and see how that propagates out and gets to either a smaller error or sometimes a much larger error. And so this is where that, as Ignacio was trying to get to, is there a way that we can express the uncertainty on a per pixel basis so that when we feed that into the machine learning algorithms, it can take that as an input and appropriately weight that as an uncertainty and then propagate that through yet the next set of the algorithms. And then when we get out of that, we get some bar chart, some histogram, or whatever else comes out of it. We can then say, put some uncertainties on that. I think that uncertainty is something that we really need to start thinking about in terms of when we get some answer to someone at the end of the day and they're going to make some decision. I want them to be informed about the error and uncertainty in that, and are they making the right decision?
I think that's key in the sense of communicating that information about what trade-offs and what trade space has been made, not only so that downstream algorithms can take it into account, but also because then the marketplace can examine different products and making a choice as to what's best fit for them, and such that it'll drive, we don't really know what is the need in the marketplace, but if you can describe it in a way that allows for the end user to make a trade space in a market-driven way, that seems to me a solvable, or at least, otherwise, we're never going to decide, right? We're going to advocate for ourselves, but the market to decide based on good information in a way they can understand it.
Thank you, Mike.
One last question, and we're going to take a little break.
Yeah, my question was actually very much related to what you were describing right now, so that the marketplace decides what they want or what kind of uncertainty they want, but first they need to know what they're getting, so what are their options in terms of uncertainty. And if we get that,
we can connect pricing to that, or you can relate uncertainty to the amount of time that you wait until you get your result, or to the amount of time that you wait after acquisition to get some result. And with that, then we can also explore things like doing the atmospheric correction on 160 meter pixel for Sentinel-2. So a much lower resolution, but much faster and much cheaper. And maybe we will get to, I don't know, plus minus 3%, whereas full Sentinel will give you 2.5%. But for a lot of people, this will be good enough. And if you get that data faster, and if this data is much cheaper to process and download, that still has great value.
We have across the hallway in the room to the right.
So across the hallway on the room to the right, the STAC guys are doing essentially an open house, open STAC, for those of you in the room who want to possibly skip the next section and go there to learn more about STAC in practice, right? So I'm offering that, and I think with that we should thank the panel and take a little break until 4 for that last block. Great discussion. Thank you.
Cheers. Thanks.
Awesome. Thank you. It's pretty good. Cool. Thanks for the good point.